Good afternoon, everybody. Welcome to the CRM-ISM colloquium this afternoon. It is with great pleasure that I'll introduce to you today Professor Sara Faridi from Dalhousie University. Today's colloquium celebrates also May 12th, which is the Women Mathematics Day, which is the birthday of Mariam Mirzakhani. And we are, in fact, happy to have a sample of research by a woman mathematician. Professor Faridi is a well-known expert in commutative algebra and combinatorics aspect of commutative algebra. And she's no foreigner to Montreal because she actually did spend some time here as an answer postdoctoral fellow at UQAM. So please, Sarah.
So hi, thank you so much for coming out here. It's I consider Montreal my home and Lassim actually my family, but I don't see anyone from Lassim here. So you guys are Lassim affiliated, but neither one of you are at Lassim. They're like a real family. So it's really great to be in Montreal. It's great to be at CRM. Thank you so much for inviting me. I am going to talk about a project I started doing with during a Women in Commutative Algebra retreat at Banff. And the idea was this is what we call WICA 1. The idea was for groups, women are underrepresented minorities in mathematics, and for groups to get together. Women would typically pass their PhDs and more in the professional setting so that they can have collaborative research ongoing despite the many, many challenges that we all face in administration, family raising, and so on. And a lot of the challenges are common nowadays to both men and women. So it was a great initiative. Nowadays, there are a lot more conferences like that for everyone. And it was right before the pandemic too. So as a result of it, the pandemic was, I have to say, a lot of fun for me because I got to work. There were no classes for a while. And this is before Zoom became a thing. And suddenly I was glued to the computer. I had lots of time to think about this project. The project we started working on, and oh, by the way, so now I've organized, we just had the second WICA. And I was an organizer in Trento, Italy, and we're having the third one in Oaxaca in a few weeks. And it's now a global thing with lots of people from everywhere. So I should really thank the organizers of the first ones for setting this initiative. Yeah, so the project we were working on was basically the idea was we have a group, there were 7 of us in our group, 2 of us group leaders, and what kind of thing can we do that uses the expertise of everyone in the group, but also is kind of innovative. And so I was doing combinatorial resolutions at the same time, studying free resolutions of monomial ideals using combinatorics and algebraic topology. And my colleague Susan Morey, who was my co-leader, is a commutative algebraist expert in Riesz algebras, and which is something I had also done during my graduate work. And Riesz algebras are algebras that you use to study resolution of singularities. So they are the description of a Riesz algebra is in terms of powers of ideals. And so we thought we should, and Susan Morey is an expert in edge ideals and graphs. She knows lots about graphs. So we decided to study resolutions of powers of ideals using graphs. And it became a starting point for a huge project that now has many, many people on it. And I'm away and with many groups all the time doing different parts of the project. So I thought for today, it's fun to kind of tell you the beginning of the project and tell you what is a free resolution. I don't know what people's backgrounds are, so I'm not going to. My ambition is to basically get you to appreciate a free resolution. And another reason I picked this topic is that the main method and the first thing that starts this adventure is the work of a female mathematician, Diana Taylor, who was a student of Irv Kaplansky, I think, in University of Chicago, graduated in the 1960s, with a thesis that basically is the cornerstone of combinatorial commutative algebra nowadays. And then she disappeared from the realm of mathematics. I happened, when I was a graduate student, I arrived at Brandeis University in 1994. I happened to share an office with her daughter-in-law, and just randomly, and she was telling me about her mother-in-law, who also was a mathematician, but I didn't know anything about commutative algebra at the time. I thought I would do analysis. So I didn't really appreciate any of this until later on. I went to Michigan and I realized that she's a legend and no one knows where she was. Like, all these big shots were talking about, like, you know, where is Diana Taylor? She disappeared. And I remember once in a class, I said, well, she's in Ohio. I know where she is, but she had disappeared and she had no idea how important her work had been and how inspiring. And so she passed away a few years ago, but she was very, very pleased. Her son is a mathematician in combinatorics, actually, and her daughter-in-law is a mathematician. And they kind of carried the news to her about what a big impact she had made. And so I find this is a great story to tell to celebrate this occasion. And on that note, let me get started. So first of all, I want to tell you about, maybe I should ask, do people here, how many people here know about commutative algebra, algebraic geometry? Like, I know some big names, but
everyone knows everything by heart.
I'll take that as a joke. So maybe I should define it. I should define theoretical. Yeah. Okay. So okay. So a lot of old mathematics, as if you read Galois theory, whatever, it always goes back to polynomials, finding solutions of polynomials. So if you have a bunch of polynomials and you want to look at you want to solve a system of polynomial equations, you can actually, if you stare at them long enough, you realize that basically you can look at a whole set of polynomials and find all of their solutions at the same time. And the solutions are the same as the first ones that you were looking at, the first finite number of ones. So let's say you have polynomials f1 and f2, and they belong to, they have complex coefficients, take any field, it doesn't matter, and n variables. And note that the solutions, common solutions to f1 and f2, if you set both of them equal to 0, is the same as the common solution set to this set of polynomials, g1 f1 plus g2 f2, where g1 and g2 are any other two polynomials. Let's call this S, or an S. So for example, if you're looking at, like, for example, if f1 is the polynomial x1 squared plus x2 squared minus 1, and f2 is x1 times x2, then the common zero set of these two is going to be, I guess, 1, 0. If I set f1 equal to 0 and f2 equal to 0, as usual, I've just made up an example. So I think the common zero set of these two is going to be the points 1, 0 and 0, 1. For example, 1, 0, 0, 1, etc. And 0, 0, 0, 0 doesn't work here. And if you make this set, this set is going to be the ideal generated by f1 and f2. So I'm going to call it f1, comma, f2. And this means ideal generated by f1 and f2. Okay, these boards are smaller than I'm used to. Then the solution set of these two is, so this common solution set is the same as the solution set of all polynomials in the ideal generated by F1 and F2. And you can do this for any number of polynomials. But then you might be interested in a common solution set of a whole bunch of polynomials, infinitely many polynomials. So there's something called Hilbert's basis theorem that tells us that you still only need to worry about a finite number of polynomials. You can look at that big ideal, and basically the solution set is going to come down to studying a finite solutions to a finite number of polynomials. So Hilbert's basis theorem, it says that every ideal in this polynomial ring is finitely generated. So it says that basically, i.e., solutions to any set of polynomials, finite or infinite, can be studied by a finite number of them. Okay. Many methods developed to find solution sets of polynomials, like there's linear programming, matrices, etc., and etc. And generally, it's not so much is known. Algebraic geometry is basically the field that uses geometry and algebra to study these solution sets. So there are tools in algebra that you can use to find information about these solution sets. The thing about ideals is that even though we know they're finitely generated, the generators are not linearly independent. So the best behavior you can expect is finding matrices, and the matrices come from linearly independent objects. But these generators are not linearly independent. So what you do typically is you model them with linearly independent objects. So I'm going to talk about free modules. So a free module is like a module is like a vector space, but you can pick your coefficients rather to be in a field. You can pick them to be in a ring. So an ideal is a module. Typically, every element of an ideal is of the form, when you have a finitely generated ideal, it's a linear combination of the generators, but the coefficients can, rather than scalars, they can be also polynomials. So rather than this F1 and F2, you can pick abstract elements, and that makes a module. You have to keep some rules in mind about distribution and addition, but a module is basically an abelian group. Abelian group means you can take your coefficients to be integers, and then you expand your coefficient sets, and you get, in this case, polynomials as your coefficients. So a free module is a module that has a basis. That means this F1, so it's an abstract concept. So I'm not saying that my F1 is x1 squared plus x2 squared minus 1. So maybe I should do an example here. Oh, and there's some chalk, color chalk. That's good. So for example, let me see if I have an example actually that will continue. Yeah, let's do x, y, and x squared. If I take F1 is xy, and F2 is x squared, then you see that these two are not linearly independent because they have this relation. Because you can write x times F1, and you can write y times F2, and you get the same thing. So they have this relation. And linear independence means the only way you can get a 0 is that you multiply by 0 in your basis. So this F1 and F2 are not linearly independent. They have this relation. This relation is called a syzygy. Okay? So free resolutions are study of syzygies. That means relations between generators of a module in general. And this is called the first syzygy. This is, in fact, first syzygy of the ideal I So I'm now making it all formal and fancy, generated by F1 and F2. So now we have formal language for it. And there's a second syzygy and there's a third syzygy, but the second syzygy is also the first syzygy of something else. Basically, the whole idea of building a free resolution is to find the first syzygy of something, right? So I'm gonna find this, I'm gonna now do some stuff, write it up, I'm gonna compute a kernel, and then I'm gonna do the first syzygy of that kernel, which will be the second syzygy of this ideal, et cetera, et cetera. So the main idea is this relation, okay? My free resolution is going to be encoding these relations. Okay, so what am I going to do? So in commutative algebra, what you do a lot is that you can't study something, you map a free module to it. In this case, I have my generators F1 and F2. I pick two abstract basis elements. I make an free R module. And let me, sorry, S module, because I called it S. And let me take the basis to be the canonical basis elements. I can pick whatever I want. E1 is 1, 0, and E2 is 0, 1. And I'm going to make this homomorphism. Make an onto map, basically. This is a surjective homomorphism that takes from the module generated by E1, direct sum the module generated by E2, which just basically means the module generated by E1 and E2 in this case, but they're free, so I can write it this way, to F1, F2. And what it does is takes E1 to F1, and it takes E2 to F2. Okay? And then I'm going to stare at this a little bit. So I'm going to call this S2. Two copies of S. If S were a vector space, it would be a two-dimensional vector space C2, like K2. So now I have my ideal is a homomorphic image of a free module. This is a surjective map. And because, so this map is S linear. It's a homomorphism of S modules. That means coefficients all go through. E1 goes to F1, E2 goes to F2, and otherwise whatever you multiply for goes directly through. So in particular, I'm going to look at the kernel of this map. And the kernel of this map, let's call this map D. The kernel of D is generated by, well, it contains for sure, it contains, who does it contain? So I keep my coefficients. So basically, if I take, where are my relations there? Yeah, if I take x times E1 and y times E2, let's do d of x E1 minus y E2 is going to give me x F1, because E1 goes to F1, and y F2, and I already established that that is 0. So basically, the kernel is going to have my relations generated by my relation. I didn't prove it was generated by that. Well, just take my word for it. So this is a hard problem, actually, finding generators. And this is what makes computing resolutions difficult. Okay? So now I am going to do the same here. I'm going to just build a resolution for you. So this was F1, F2. I mapped S2 to it. I call this D. Now let me call this D, D1. Because I want to do it again. This is surjective. I'm now going to, it has a kernel. And if I put the kernel here, I'm going to put it down here, x E1 minus y E2. This is also now, this is injective, right? Because the kernel is contained in that. So I have an exact sequence. But a free resolution is an exact sequence of free modules. So I'm going to repeat what I did for this one. I'm going to calculate the first syzygy of this one. There's only one of them, so that's not hard. It's just S. So If you look at these, in homological algebra, a lot of long exact sequences come down to short exact sequences, like little short exact sequences. This is one of them. So this is the first syzygy. The first syzygy of this one is 0, basically. So I'm going to compose these two maps. This is my D2. And after this, there is no kernel. Just take my word for it. Okay. So here what I've done is that I've made an exact sequence. So exact sequence of 3 S modules. Exact sequence means that the kernel of each map is equal to the image of the previous map. Okay, so that means kernel of D1 is image of D2. Exact sequence of 3 modules ending at F1, F2. So, and that's the definition of a free resolution. I have built a free resolution of this ideal. This is an example of a free resolution of I. Okay? So a free resolution can be as big as you want it to be, because I can take, this is just a sequence of 3 modules with some maps between them. In fact, for all practical purposes, you can throw away the S. You can model this using just vector spaces. This D2 is a matrix. This D1 is a matrix, and you can make them, there is an elegant way to write them for nice enough objects into just matrices in linear algebra. But the thing is that this can be as big as you want it to be. Like this ideal generated by 2 things, I found this resolution. I think it's the smallest one, but actually I didn't compute that, so it doesn't matter. But I want to tell you is that I can make it as big as I want to. I can add an S. This is a trivial sequence, just identity. I can add it here. This becomes S2 and an S. Continue this indefinitely. Make it as big as I want it to be. There is no upper bound, really, by adding trivialities. And these trivialities give you identities inside the matrices. If you look at them, we'll look at matrices in a minute. Okay? What I'm interested in is a minimal free resolution. A minimal free resolution has different identical definitions, but basically the idea is that what is the smallest possible ranks you can get? That's the minimal free resolution. So, oh, maybe I should, right. So this is a good time also to mention that even though I can make these as big as possible, Hilbert's, this is all the same paper. This is the one big paper of Hilbert's syzygy theorem. Says that basically an ideal in a polynomial ring A of x1 to xn. Let's call it C as before. Has a free resolution of length less than or equal to n. So even though you can make this as big as possible, there is a bound for polynomials, and in more generally for local rings and so on. But we're just looking at this situation. Now the bound is n. Okay. And right. So the question is, how small can it get? So a minimal free resolution of I is an exact sequence, let me say S of a free S modules. And I'm going to throw an I at the end here, but really the free resolution is really free modules, so it really starts from here. So the word free refers to the fact that these beta i's are the smallest possible ranks that you can get. So we call these beta i's Betty numbers of I. and they're invariants of the ideal or the module if they're invariants, because basically, here's a fact, a minimal free resolution is unique up to isomorphism of complexes. That means you can find free resolutions in different ways. The minimal ones are you're always going to get the same ones. That means the ranks are going to be the same. So being unique up to isomorphism means that if you have another free resolution like this, then the length is going to be the same. And there's going to be an isomorphism between every component so that the diagrams commute. It's a homological algebra diagram chasing. So what this does is that it makes those betas unique. So the beta I, beta 0 to beta p are unique. And they're called the Betty numbers. And p is unique, called the projective dimension. Okay, and the way that I showed you that I built a resolution like the canonical way by finding generators of the ideal minimal generators, finding the syzygies, and then calculate the kernel, finding the next syzygy. I built everything based on minimal generating sets, so that guarantees me that I'm going to get a minimal free resolution. It's highly impractical, but it's the most canonical way to do it, and you can show that the result, the outcome is minimal. Maybe this is a good time to stop for questions.
P is the length, or is the
P is the length of the resolution. Yeah. So these numbers are invariants because, like a lot of formulas that you see in commutative algebra and algebraic geometry, these numbers appear in them. So the whole industry calculating Betty numbers and projective dimension and regularity, which also comes from here. And I'm not going to really talk about that. See, Betty numbers and projective dimension and so on, I'm going to show you. They can be, you can topologically describe them. Regularity, which I didn't talk about, it's the size of how high the degrees here are, but I haven't graded this yet. And I will not grade it really, I will multi-grade it. It's about how fast these can be. And that one is, you need one extra topological step to describe it, and that one extra duality theory. And the duality theory is not developed yet, like in the literature. So it's not as easy to give a nice talk about the topology of regularity, in my view, in my experience. I mean, I'm sure some people have a better perspective. I wanted to, while we're here, I just wanted to say that things can go awfully wrong if you take your polynomial ring and just go mod one polynomial. So you no longer have the finite, you no longer guarantee the finite resolution. Everything changes. So the world is really nice when you're just over a polynomial ring. Any questions? Yeah.
So P is less than or equal n, but in practice could be any inequality. So P and N, P is less than or equal n in this case?
Yeah, P is, oh yeah, thank you. Yeah. I talked about this, I didn't write it down, yeah. So Hilbert's syzygy theorem says that P is always less than or equal to the number of variables in your ring. Yeah.
In practice, you can see any possible value less.
Yeah. You can do project. So this whole Wicca project that I was talking about started from projective dimension 1, which is the shortest one you can get. And based on a master's thesis of one of my students at Dalhousie, who is now in Concordia, Ben, who is not here in this talk, but I'm hoping maybe he's out there. But Ben's thesis plays a big role in everything we did. Any questions? Okay, so, all right, so we want to calculate these things, and I want to say that they're many ways that people like basically develop their careers to calculating Bethe numbers, projective dimension, and so on, are finding descriptions of them and characterizations of them and so on. A lot of computational algebra is dedicated to that. Grosvenor basis theory, one of the things it does is like, one of the first things Grosvenor basis theory does is finding generators for ideals. The ideal membership problem is always like one of the first things you teach in Grosvenor basis theory. But it's expensive. Like if you try to compute anything with 3 generators, and in this project that I'm talking about is concerned with powers of ideals. If you try to do anything with more than like 3 generators, you're going to stop. Already with 3 generators, you can't go very far. So it takes a lot of computational power. And then there are many other different methods people have developed, including combinatorics. So I'm going to talk about Diana Taylor's work. Yeah.
The number of generators, that's sort of measure the size of the problem with number of variables.
I would say mostly the number of generators. I am extremely unqualified to answer this question because like this is my area, right? So I know there are people who really specialize in this. But my experience is the number of variables honestly doesn't matter that much, I find, when you're doing when you're analyzing polynomials. I'm not a computations master, so.
These are kind of things you would do on a computer.
Yeah, on Macaulay 2 is usually what we use. Yeah. There's also Cocoa, which is better for Hilbert functions and things like that. But generally for syzygies and so on, it's Macaulay 2. And generally, every server I use freezes pretty much at the 4th power, even if you have very few generators. So. And like I say, I'm not really extremely qualified, but I'm pretty sure that the limit is low. You have to have theory for the calculations. You can't just hope that the computer does everything. Okay, so all right, yeah, Taylor's thesis. Okay, so Diana Taylor, I think it's a 1966 thesis. Basically what she said is that, okay, so right, I'm going to start talking about monomial ideals. Diana Taylor's thesis was about monomial ideals. So monomial means one term, polynomial with one term, products of variables. Monomial ideal means an ideal whose generating set is monomials. But of course, the members are going to be just polynomials with those monomials as terms. So what she noticed is that you can construct, this is in a nutshell, a free resolution of an ideal, and again, in a polynomial ring, generated by Q monomials by, this is not a language that Diana Taylor used, but it's okay for today, by homogenizing the simplicial chain complex of simplex on Q vertices. Okay, so I have an ideal generated by Q monomials. A simplex generated by Q vertices means that it's the convex hull of Q points in affine space. You can think of it like that. Or you can think of an abstract simplex or simplicial complex as a set of Q vertices. A set of two power set of Q vertices. Okay, and by the way, this is giving an answer to your question. It's the number of generators that matters, right? It doesn't matter. So what this is saying is that the length of your resolution is bounded by Q, by the number of generators of a monomial ideal. Okay, so let's do this for I'm going to show you how this works for 3 generators. So let me pick an ideal I generated by XY, YZ, ZU. On this side, a simplex on Q is 3 vertices. So it's a triangle. Convex hull of 3 points. Or all possible subsets of 3 points. And I would like you to think of it this way because I'm going to then talk about simplicial complexes in general. So 1, 2, 3. There is a 3 face. That means the set 1, 2, 3. And 3 edges, 1, 2, 1, 3, 2, 3. And then 3 vertices, 1, 2, 3. And also the empty space, which will appear at the resolution. Typically, when you do resolution of S mod I, you have an S sitting here corresponding to this empty face. Those are small technicalities. But anyway, what I'm going to do is I'm going to call these generators M1, M2, M3. And I'm going to label vertex 1 with M1, vertex 2 with M2, and vertex 3 with M3. Okay, and then I'm going to label each one of the faces with the LCM of the vertices. So this is going to be LCM of M1 and M3, for example. I won't do the whole thing. Okay, so in algebraic topology, to this we associate a chain complex. And the chain complex consists of basically maps. Like this is a triangle. The triangle, you put an orientation, that means you give every face a direction, and then you compute the boundary of every face. Everything you see here is a face. So the boundary of the triangle is these 3 edges. So the boundary of the triangle is going to be this plus this minus that, according to whatever orientation you pick or whatever field you're over. You can do this even over Z. And the boundary of this edge, for example, is going to be like this vertex minus that vertex. Okay, so it's a map. You can think of it as a map of a collection of a sequence of group homomorphisms. You can think of it as a sequence of vector space maps. I'm going to do it over a field K. So the simplicial chain complex of a triangle is the following. So this one so I'm not going to get all of my entries. This is a sequence of 1s and -1s, which I always get wrong, but so forgive me. So this is K for the empty face, 3 vertices, 3 edges, and 1 triangle, and nothing else. Okay, so that's the map. And the matrices are saying who is a boundary of whom. So if I call this E1, E2, E3, then what this is really is basis E1, O plus basis E2, basis E3, and based on, sorry, this one is actually the vertices. Vertex 1, let me do this again. So vertex 1, O plus, vertex 2. It's really just a map of linear transformations between vector spaces. And then E1, E2, E3. And I really shouldn't have done that because now my matrix will be wrong. I already had adjusted my matrix and I randomly labeled this. So up to a permutation of rows and columns, actually columns, I am going to have the following matrix. 1, -1, 0, 0, 1, -1, and 1, 0, -1. Here I'm going to have 1, 1, 1. And here I'm going to have 1, -1, 1. And because I probably got the order wrong, I'm going to erase this and call it K3 again. I'm going to erase this one and call it K3 again. So this way, because someone in the audience will do the calculation. So K3, K3. So this corresponds to some edge going to one vertex minus the other, the two end vertices. So I can homogenize this. And the homogenization is an actual homogenization of the map. So I'll just show you in practice what it looks like. So 0 to now S, which is my polynomial ring. So S is going to be K of X, Y, Z, U. So S to S3 to S3 to S. And here again, now my generators are going to go in the first map. So I'll just do this one here. This one becomes U. This one becomes X. This one becomes -1. So every time I have a map between two faces, I take a quotient of their new labels with these LCMs. And I'll do this one too. So this is Z, -X, 0, 0, U, -Y, and ZU, 0, and -XY. Okay, and the reason I picked this example here is that because I'm getting a non-minimal resolution, and I just want to demonstrate that to you here. So if you know the other definitions of a minimal resolution, or you detect what I was telling you about having an identity map in there, you will notice here there is a scalar here. This scalar means I have an S to S without any change of multiplying by anything. So, and really this S here, the way I can write it is I notice, let me label this. The LCM of these three monomials is X, Y, Z, U, right? This one is, M1 is X, Y. This one is Z, U. And this M2 is Y, Z. And this LCM of M1 and M3 is actually, again, X, Y, Z, U. And what you're seeing here is X, Y, Z, U mapping to X, Y, Z, U. That's where the 1 comes from. So this S3 here is really S of this edge, which has label X, Y, Z. O plus S of this edge, which is label Y, Z, U. O plus, this is called a multigrading, which keeps track of which faces and what monomials we're having. S of this face, which is S of X, Y, Z, U. This one is just S of X, Y, Z, U. Here, this is extra. So this resolution is not minimal, and the Taylor resolution is usually not minimal. However, sometimes it is minimal. So the Taylor resolution is an upper bound for resolutions, minimal resolutions of all monomial ideals. It's even a sharp upper bound. Okay. So now I'm going to do a couple of things. How much time do I have?
Another 10, 15 minutes.
Okay. So I'm going to do a couple of things here. First of all, let's look at this here again, this example. So what happened is that I have this ideal generated by 3 monomials, and I made a Taylor resolution of it. So you can do this for Q monomials, whatever you want, by just the same labeling. And I notice I have repeated labels, which are leading to a trivial short sequence inside here, making the resolution non-minimal. So kind of late in the 80s and early 90s and so on, people started looking at this. So the notion of general cellular resolutions and simplicial resolutions. So here the question you're asking is, I equal to XY, YZ, ZU has a Taylor resolution, which is not, and you can tell why. Can you do better with topology? So there are these two faces over there who are being very offensive by sharing the same label. You see, the thing about a simplex is that it's acyclic. It doesn't have any cycles inside it. So this simplicial chain complex that it gives you is an exact sequence. So the idea here is, let's remove these two. And then let's use the simplicial chain complex of whatever is remaining. Do we have a resolution? Let's homogenize that. And the answer is yes. So this is work of Bayer and Sturmfels. And then for the cellular case, and then Bayer, Peva, Sturmfels. So we can do, and the can do means, the quotes there means how can we do the same by labeling vertices of any acyclic simplicial complex. So in this case, I'm going to remove those two faces, and then Bayer and Hilbert Sturmfels, their results tell me that in this case, it's kind of exactly so this supports resolution of supports means that the simplicial chain map can be homogenized to give you a free resolution. So this here now, see, the thing you have here is that once you have a simplicial complex, Taylor's result, what does it tell you? It tells you that Betty numbers are bounded by binomial coefficients. So it gives you a sharp upper bound for values of Betty numbers. So beta I is always less than or equal to the number of faces of dimension I of a simplex, which is if you choose I, or size I, depending if you're resolving I or S mod I, okay? So it gives us binomial bounds. But you see that binomial bound is not necessarily the best for this ideal. In this case, for a simplex, you get 1, 3, 3, 1. But actually what you needed was really just, you need the 3, and the 1 is the empty set, 1, 3, 2, that's it. Projective dimension is 2. 2 edges are enough, you don't even need a triangle. So your projective dimension is much lower. This is a minimal resolution. Why is it minimal? Because when you see, as you see there, to get a 1 in the matrix, you need to have the same labels, and here no two embedded things have the same label. So this is X, Y, Z, and this one is Y, Z, U. And this is in fact the smallest you can get. It's called a scarf complex. Do you have a question?
I'm trying to see the two in the, like this is saying that I should have K goes to K3 goes to K2, and then K.
This one, oh, for this one?
Yeah, because I see the one with the 1 is.
So K is the empty set, 1 empty face, 3 vertices, 2 edges.
Okay, then the resolution will be.
The resolution will be K, K3, K2.
Okay.
So basically, because you kill this, right? Once you kill this, you kill this. So it becomes finite. So actually, this is where we started in BAM. So I was telling you about Ben Hersey. If you see, if your ideal has a resolution supported on a graph, it means it has projective dimension 1. Forget about this one here, it's always there. So there's always stops after edges, right? And Ben, in his thesis, he proved that every ideal of projective dimension 1 has a resolution supported on a graph. So basically characterize this. And this is not true for projective dimension 2. See, if you take any acyclic simplicial complex, you can build something called a nearly scarf ideal that has a minimal free resolution and more supported on that complex. So one way is clear. But if you take a ideal, a monomial ideal, it might not even have a simplicial resolution or a cellular resolution, or on a CW complex, may not have a topological resolution at all. There are efforts being made into making like topological descriptions, but there are actually counterexamples by Mauricio Velasco of huge ideals that do not admit cellular resolutions. Already in projective dimension 2, we know that there are ideals who do not have simplicial resolutions. So this a cell complex, the difference between a simplicial complex and a cell complex is the difference between a triangle and a square. A triangle is a two-dimensional object that with 3 vertices, and it contains all possible edges between those vertices. A square is also a two-dimensional object. It just has a more general definition. You can define it in terms of intersection of hyperplanes, convex hull of points, etc. But this is a two-dimensional cell complex, but not simplicial, because it's missing AB, missing that edge. So for generators, it's another, like, there are many things going on, but for some ideals, we can show that they always have cellular resolutions with small numbers of generators. In general, none of it is true. Okay, so maybe in a nutshell, because I didn't really get to say anything about what we did in BAM, but we started from here. And we said, okay, take an ideal that has a resolution supported on a graph. What about the square of the ideal? What about the third power of the ideal? Can you say anything about that? And so while we started, let me tell you a little story here. So we started with this. We took this square. And when we took this square, we didn't know what to do with it anymore because the square was a bigger resolution. So we had to describe it. So you take the Taylor complex of the square. It's big, has a lot of extra stuff. So what we did is we used discrete Morse theory to shave down. So this is a way discrete Morse theory gives you a method. You start with a topological object, discrete topology. It gives you something that is homotopy equivalent to what you started with by deleting faces. So we deleted lots of stuff. And we managed to show, maybe I'll do the rest by pictures. So this is what the Wicca people did. So suppose I has resolution, minimal resolution, supported on a graph, this graph. Then what about I squared? So discrete Morse theory on the simplex. So there's 3 vertices here. It's going to be the squares and the product, 6 generators, 5-dimensional object. Brought us down to this picture. And I'm drawing it for you because I'm trying to make a point. I won't label it with the vertices. Like this one is M2 squared, etc. And this is just for that example. So brought us to this picture. Of course, this is a cycle, right? So this is not going to support anything, but it wasn't like this. It was shaded. Because what discrete Morse theory gives you, it doesn't give you an exact complex. It tells you there exists a CW complex with 6 edges, 6 vertices, and 1 2-cell. But you go figure out what it is. I mean, it tells you there are gradient paths and so on you can use to say what those faces exactly are. But this was the output, and this is not even a cell complex. It's just missing stuff. But then really by following the topology a bit more, you could kind of say that actually it deforms into this picture, okay? But this was not, you don't really know your output of discrete Morse theory. I mean, it's not even guaranteed to be polyhedral. And so it could be anything. And so we then redid this whole thing using Koszul resolutions. So using algebra on ideals of linear type. So these are things that go along with Riesz algebras. Basically using Riesz algebras, noticing that the defining ideal makes a regular sequence, making a Koszul resolution of it. The Koszul resolution matched the Morse resolution that we had here. And then we could say that actually, yes, this was a resolution. And this was all of this making minimal free resolution. Okay, and as a result of this, we could describe this picture here as a product of these two graphs. So I could describe this picture as a square of that picture. So this is where basically this whole field is now going towards. How do you take a power of a topological object, which is supporting a resolution, giving you a free resolution of some ideal, and you describe it so that it's topologically sound, like it follows the laws of topology, it's acyclic, it does nice things. You can describe it as a square, a cube, a power, any power, and it still supports a minimal free resolution. So there's lots and lots of lots. In particular, one particular group that is working now, so we brought in Art Duval is from combinatorial topology, and then a bunch of other people are now involved, and we're doing powers of a simplex. So we can do the second power of a simplex. We already did this with the Wicca group. That means a generic, something that supports the resolution of the second power of any square free. We could only do square free so far, monomial ideal, and is also a sharp bound. That is much better than the Taylor complex. By noticing that once you take a square, you create a lot of these redundant relations. And so that the third power is coming up is related to partitions, to graphs on partitions, and so on, hyperplane arrangements, polyhedral geometry. I have a whole class of grad students trying to show when is a Morse complex polyhedral. We know it's not always so far. So there's lots and lots going on here. Sorry, I didn't get very far with results, but I hope I gave you a flavor of the area.
Questions? Yeah.
If we can do I squared, what about like the product of two monomial ideals?
Yeah, that's coming next. And right now right now with one group we're looking at powers of Morse matchings. Morse resolution, Morse matching. Basically, when you have Morse matching, how do you take a power that next to that is how do you take a product of Morse matching things. My opinion right now is that because these Morse matchings are done with big graphs and basically set lattices, directed graphs. And so my feeling for it is that you can do a lot, but at some point, because the Morse complex gives you things like this. So to get somewhere like that, you have to take different Morse matching graphs and glue them together and then follow gradient paths inside them. So it's complex. It's yeah, I don't know, but we're working on it.
So you have an ideal of minimum projection length 1. You always have a graph, no matter how many vertices.
Yes.
You know other examples when you have a graph, but it's not length 1 projection.
No, because when you say your well, it could be projective dimension 0. I mean, when you say your resolution is supported on a graph, that means it starts with, for example, 3 vertices. That's a K3. And then 2 edges, that's a K2, and then there's nothing else. So your projective dimension becomes 1. Maybe it wasn't minimal, so it's 0. Yeah.
Thank you very much for your talk. I have a question. So I don't work on Morse theory, but when I see that attached, I know there's sometimes there will be these inequalities. You mentioned so many qualities for value numbers. Does applying this theory, does it give you some?
Yeah. So basically every time you're building okay, the general thing you want to keep in mind is that you know that everything has a simplex resolution, but that is huge, those bounds for Betty numbers, way too huge. You know that not everything has a cellular resolution, so you can't minimal cellular resolution. So you can't necessarily get to the Betty number. So the idea is that squeeze down your simplex as much as possible using whatever method you have so that you can get a minimal free resolution as close as a free resolution as close as possible to the minimal one. And if you do that nicely in a combinatorial point of view, then you have beautiful bounds on Betty numbers. Because at each time the number of faces is giving you a bound on the ith number of I faces is a bound on the ith Betty number. And if it's minimal, then it's equal to the ith